Good morning, afternoon, evening, everyone. I'm Julien Michel. I will be talking about the results submitted by my group at the University of Edinburgh. We're going to talk only about alchemical free energy calculation and the free energy prediction we did using our custom software, SAMD. So before we jump in details, I want to highlight the input of group member Antonia May and Jordi Juarez Jimenez for this particular D3R ground challenge. So the techniques that have been used in this competition from our group are mostly built around two tools. One is called FE Setups. That's a software we used to prepare our input file for alchemical free energy calculations. That generates input for a range of different molecular simulation package. The particular one we are using here for this ground challenge is called SAMD, and that's a single topology alchemical free energy calculation engine that has been created by putting together two different software libraries, and here we're taking advantage of the OpenMM library to run this free energy calculation on GPUs so we can have a reasonable turnaround. This is a depiction of the workflow we've been using for binding affinity prediction in D3R. This is a semi-automated workflow in the sense that we have been generating 3D poses for our free energy calculation mainly manually. That was done by Jordi through analysis of known structures. We also need to do some steps of the setup manually where we decide how we map free energy calculation between compounds. And the rest of the workflow is catered for by a different piece of software that prepares the input, perform the simulation, perform the analysis, put together the result for the data set. So before we jumped into D3R, we wanted to test our workflow through retrospective studies of compounds present in the literature. And so we ran these two different series called LEAD D1 and LEAD D2 through our workflow. The first one is a small data set of 8 compounds. We had to deal with multiple binding modes, so that leads to more calculations, and some additional 1 add-on to closed cycles. LEAD D2 was a larger benzimidazole set. These are the results from our retrospective analysis. So this is all based on poses modeled from available X-ray data. We saw overall reasonable correlation in terms of R descriptors, and a fairly high mean unsigned error, which worried us a little bit. So we decided to dig in this before doing our D3R prediction. And looking back at trends, we saw that we felt that whereas non-polar to non-polar change in our free energy calculation seemed reasonably well behaved, for instance, cyclohexyl to tetrahydropyran here. You see this the experimental data, the calculated free energy change. That seemed all right, but when we were dealing with non-polar to polar change, for instance, or dichloropyridine to chloroamide, we saw some over-exaggerated change in energetics. And some extreme case here where we are adding carboxylic acid, so changing the net charge here gave us non-sensible free energy change. So we thought at this stage that maybe some of what we were seeing was due to the use of fixed charge classical force field. And so of course we would like to be able to run calculation that account for these effects, but we don't really have an off-the-shelf great tool to do that. And so given the constraint of the exercise, we came up with a very simple method to try to capture some of these effects. And so what we did effectively is to correct our calculated relative binding free energies by calculating free energy change for scaling down partial charge on our ligand, either bound to the ligand or in solution, and doing that for two compounds A, B involved in a relative binding free energy gave us a way to provide so-called corrected binding free energies. And by playing a bit with this adjustable scaling parameter, we did find that we could significantly reduce the mean unsigned error on the first data set while maintaining the same correlation. For the second data set, there weren't a lot of change. The correlation dropped a little bit, and we thought maybe this is because this one contained more nonpolar groups. And moving on to our D3R submissions. So we made submission at two stages. Stage one, we had some free energies from our code based on best guess for binding modes. We also made a so-called expert opinion submission based on me essentially guessing binding energies, and that was done after we had done the D1, D2 calculation. So we had some idea of the literature source. So we're not completely blind to the system, but we did those before we ran any free energy calculation on the D3R sets to avoid mixing the two approach. And in stage two, we repeated essentially our stage one protocol, but started from poses recreated after we were made aware of the actual binding pose of some of its compounds. And we had a bit more time, so we could converge our free energies by doing multiple repeats a little bit better. This is a summary of our results using a so-called expert opinion submission. So only done at stage one for set one or set two compound. These are the results for the full data set. You see in terms of mean error, it's about 1.7 kcal per mole. The R value is very low. This is a subgroup where we only look at compounds that have the same net charge. You see its performance is similar. For set 2, same analysis, about 1.8 kcal per mole mean error. The same net charge subgroup has an even lower R values than the full set. But overall, there was little predictive power, which was a little bit surprising, in fact. So stage one binding mode prediction, we did not submit those, but we had to guess binding modes for some of the compounds to run our free energy calculation. You can see that for set one, our guess was reasonably good. Ligand aligned fairly well with the actual crystal pose. In set two, we didn't do that well, and the carboxylic acid here, or indeed the thiophene or benzyl ring on the sulfonamide, were not correctly positioned, so that would have certainly affected the accuracy of the free energy predictions. These are our stage one results for set one and set two group. So you can see that set one, our full data set, the mean error is higher, worse than our expert prediction. In terms of correlation, it's also very low and comparable. If you focus on this group with the same net charge, you see that the results improve somewhat. Set 2 contain multiple compounds with different net charge, and that also significantly messes up the free energy predictions. But if you do your calculation on the same net charge group, the mean error drops considerably, and there is a little bit, although it's a very low R value. These are the results we got, and moving on to stage 2 of the competition. What you can see that, again, if we consider a full data set and mix compounds with different net charge, we have high mean error. The same net charge group, the results are better behaved. Using our scaling trick here did not really lead to any improvement compared to our prediction with our standard force field. It actually also makes results worse for compounds that do not change net charge. So that didn't seem to be a good idea on this data set. For set 2, the full set is again, the results are very poor. but we were expecting that. And if we focus on the groups with the same net charge that we submitted separately, you see that again the mean error is much lower, the R value is significantly higher than in this case. Looking at the effect of scaling here, in that case you can see that allows us to treat the full set and get reasonable R value, but that's mostly because through that protocol we're able to deal with compounds with different net charge. However, if you compare the results here and here, you see that it's coming at the expense of predictive power for compounds within the same net charge group. So overall, if we look at the performance at stage 1, stage 2, well, for set 1, the results in terms of R value, like for everyone, were not really great. Our predictions tend to be mid-ranked. Some of those that deal with multiple charge, net charge issue rank a little bit better. Moving on to stage 2, the results improved barely for set 1. For set 2, we did see some improvement going from stage 1 to stage 2, and we're not completely sure yet why, but we suspect it could be done to the more accurate binding mode that we used at the second stage of the competition. And finally, a couple of lessons learned from this exercise. So one thing you can see on this plot here, these are our calculated relative free energies with respect to the change of net charge on the ligand. So you can see there is clearly a systematic effect that needs to be corrected. So that's something we are looking at the moment. Now, it's something we were expecting from our retrospective analysis, but what we proposed here in this competition, the charge scaling approach, is not something I would recommend to use. To perform this calculation, we had to deal with further automation of our tools. We ended up automating the analysis of our free energies. But we realized that it's still a significant effort for us at the stage to perform this calculation. There is quite a significant human effort. And we want to automate further our workflow and address these various issues here so that ultimately we can remove more and more of the human element in this calculation and eventually hopefully have some very automated way of doing these predictions. And I am going to just conclude with a couple of thoughts on the overall state of the D3R Grand Challenge. So this is the second one that we have been pursuing. And so this year, I think that the data set were really interesting and nice because they were challenging in many ways and also allowed us to really look for variability between our different methods. Now, the way we've calculated all our uncertainties in our analysis is quite a different method from the one used by the organizer to calculate error bars. So we've realized eventually that we are not actually measuring the same things. We were focused on precision and reproducibility of our protocols, whereas this analysis here is based on bootstrapping, and that's probably going to generate high error bars due to the small population of the data set. So it's just something we need to think about what exactly we want to measure with our uncertainties. And again, I mean, we have some failures. I mean, we can see that in our case, we need to deal with electrostatics better, but other cases are difficult to troubleshoot yet. And so I think it's also important to think about how this current challenge can be complemented with data sets of intermediate complexities, and I'm thinking host gas systems, for instance, where hopefully we can control and isolate the sources of error more effectively. And that's it for me. I'm going to wrap up here.